parts you can see with features you can't see. Work at the mesoscale involves components that tend to be 1 to 3 millimeters in size, but with micron-level dimensions. These tiny parts improve many devices, from airbags to digital projectors. But inspecting them is time-consuming and difficult due to a lack of appropriate measuring tools. Now, Sandia researchers have developed a better way to support small parts.
Let's see, I think I want this one.
You get a corner.
Metrology, the science of measurement, revolves around what you can touch and see. To ensure the quality of small parts, inspection involves high-precision touch-based coordinate measuring machines, or CMMs, and less precise optical systems. Currently, optical machines are calibrated with artifacts that have serious resolution limitations.
So this is a chrome on glass calibration artifact. This is fabricated using a two-dimensional technique.
Printing.
Essentially printing. Your ability to certify this limits the accuracy of the vision inspection system.
The problem is that the commercial equipment that is currently used to measure using vision equipment typically has an accuracy on the order of 1 micron or so, but the actual resolution and repeatability is 10 times better than that. And as things get smaller, more precise, you would like to be able to capture that better resolution in terms of the actual accuracy.
Sandia's artifact design was inspired by macro-scale calibration techniques, where step bars contain measurement planes at well-defined intervals. At the mesoscale, the team used bulk silicon micromachining, or etching, to fabricate a structure with geometrical features such as sharp edges that can be accurately measured with a touch system. Once the artifact's geometry is certified with a high-accuracy CMM, it can be re-evaluated on a vision machine. This allows a more accurate calibration of the optical system, which leads to better measurements of components.
These are made by silicon bulk micromachining, where you can pattern in 2 dimensions some geometry and then put it in an etchant. And the etchant is very selective. It wants to etch along certain crystal planes to make these particular geometries. So when we define the 2-dimensional pattern, we can create a 3-dimensional structure.
You have 2 planes. One's a sloped plane and one's the top surface plane, and these are defined by the crystal structure in the silicon. And they're intrinsic, so they don't change, and they're the same on every wafer. And the angle between these 2 planes doesn't change. So what we do is we touch with a CMM on the side, and we touch with a CMM on the top, and we intersect those 2 planes and find the edge. The same edge is visible very clearly under a vision system, because when you look down from the top, the light reflects back, and the sloped surface, the light reflects right off of it, so it doesn't get seen by the optical system. So that's how we go from the mechanical touch system defining the edge to the optical system locating the edge.
When the user uses our calibration artifact rather than the other calibration artifact, we will then be able to certify the accuracy of this machine to 0.2 microns, a 10-fold improvement in the accuracy just by using this rather than by purchasing a completely new system.
These images represent the improved accuracy of Sandia's 3D artifact over existing 2-dimensional vision systems. Combined with the relatively low cost of production, there's great potential for this novel design.
We have a lot of interest every time when we present it. People say, "Oh, well, I'd like to buy one. Can you give me one?" Well, unfortunately, we can't yet. We're still seeking industrial partners. But there's a lot of interest. They realize that, oh, you have the tactile method of certification, and you can then certify a visual instrument. And hey, even if I already have this piece of equipment, I can get 10 times the accuracy for free or virtually free now.